Thank you, Dr. Harish, and good morning to all the participants who are attending this particular lecture. The topic of the today's discussion is the introduction to remote sensing of Earth and planetary bodies. In fact, in this particular session, we will be learning or going through that how this remote sensing technique helps in knowing the various natural resources of Earth and help in exploring different planetary systems. Okay, if you see this particular picture, you are seeing Earth, Moon, and Mars. By seeing the picture itself, you will be able to say that which picture is of Earth, which picture is of Moon, and which picture is Mars. Obviously, the blue-looking picture with diverse color is Earth, relatively black and white picture is Moon, and the reddish-looking picture is Mars. Why such colors come out of a planet? Because of its evolutionary processes, like atmosphere and the surface feature. They provide a distinct spectral characteristic of each planet. And that is where the remote sensing help us to know their physical characteristics and the properties. We'll be learning during this particular session that how this particular techniques is used in a practical cases of knowing the property of various targets. Remote sensing, as a definition, is a science of making inference about the material objects from the measurement made at distance without coming into physical contact with the object. So when we sense anything from a distance, a remote, we call remote sensing. But it usually refers to the technology of acquiring information about Earth and planetary system from the sensors on board, either airborne or spaceborne, or this kind of platforms where you put different sensors to observe these planetary systems. The physical basis of this remote sensing lies with the fact that one chooses a spectral window in an electromagnetic spectrum spreading from the UV, optical, thermal, infrared, and microwave region. Once we choose a window called optical, we measure the reflectance, the reflecting property of the object, or when we choose the thermal infrared region, we measure the brightness temperature of the object, or when we use the microwave region, which is a relatively longer wavelength region, we either get the brightness temperature, or if we have an active sensor, we get backscattering coefficient. Now, depending upon whatever the measurement we do of reflectance, brightness, temperature, or backscattering coefficient, we use some radiative transfer modeling and image processing technique to know about the various properties of land, ocean, atmosphere, and the planetary bodies. The basic premise, the fundamental principle by which we are able to know the property is called Planck law. So whenever a black body, or in fact, all things emit radiations when they are at certain temperature. The perfect emission of the radiation is called black body. So it emits radiation according to the Planck function, in which if you know the lambda, if you wavelength, and you know the temperature, you can know the spectral radiance coming out of the particular body. When configured in a particular wavelength region, observes the spectral radiance in that spectral region, one can invert this law to know the physical temperature of the body. Since the real bodies are not black body, they are gray bodies, they deviate from this principle. So any deviation from this, we can also compute the emissivity of the target, which again is linked to the various property of the target. There are various kinds of sensors. Some are active, some are passive. When we say active sensors, mostly they are lidar, radar, scatterometer, altimeter. It means the sensor has their own source of radiation, or where the light or the microwave signal, they are made incident on a surface, and we see the reflected part of it or scattered part of it. When we say passive sensors, they do not have any source of their own. They have only receiving signals. So whatever the surface emit, or even many times when the light falls from the sun, whatever is get reflected from it, this passive sensor detects them. They are called radiometers, they are called imaging spectrometers, uh, and they can work in any spectral window depending on the requirement of a scientist. So a spectral window is chosen. In this passive remote sensing, which is very popular, most of the remote sensing is done in passive remote sensing mode. The remote sensing of energy naturally reflected or radiated from the terrain. So whatever comes from the terrain naturally, it is a sun reflected light is also called passive radiation, where source of light is sun, and we are only receiving. Many time in night when there is no sun, we also receive the radiation emitted by the target in an infrared region, that is also called passive remote sensing. In active, as I said, they have own source of electromagnetic radiation. So light is incident upon a target and then again reflected or scattered back energy is recorded and interpreted to know the property. The scientific rationale of the remote sensing is every object has a characteristic reflectance signature. We call it spectral signature. What does it mean? It means that if I plot the reflected light in terms of reflectance of the object with respect to wavelength, say from visible to infrared to microwave region, the distribution of the reflectance with respect to wavelength is varies, and it has a characteristic variation for different targets. Like if I talk about snow, obviously we all know snow reflects a lot. So reflectance is very high, and its high reflectance is there in majority of wavelength except short wave infrared, where there is a absorption by the snow properties. The most important thing in Earth, we see the vegetation. What we see is a green, vegetation is green, and white is green, obviously, because it reflects more in the green wavelength, say 500 nanometer, as compared to the blue and red. And why it reflects more in green as compared to blue and red? Because it has a chlorophyll pigment into it, and the chlorophyll pigment has an absorption feature in red region as well as in blue region. That is why when the blue and red get absorbed, what you see is a green red, reflection more than this. But it is all for the visible region. You know, when you talk about the total spectrum, something which we cannot see, that is beyond red, called near infrared, and peculiarly this vegetation has a very high reflection as compared to visible part. Their reflection can go to 40 to 50%. And this peculiar behavior of reflection in vegetation is used in remote sensing to know its vigor in form of a index called normalized difference vegetation index, NDVI. What is this NDVI? NDVI is a measure in which the near infrared reflectance and the red what you call reflectance is taken care together, and using this contrast between these two, we are able to know the vegetation vigor. Similarly, the soil, similarly, the water has their own characteristic, and scientists has recorded and know their characteristics well in advance by conducting ground experiment, so that whenever satellite takes a picture and record this reflectance versus wavelength on board a satellite platform, scientists are able to identify that this particular feature is of this category, and we are able to know that this particular region is composed of either snow or the vegetation or the soil or the water, and even we can know the properties. But while doing this, it is not that we can do in any wavelength region. We choose some wavelength region, like for vegetation monitoring, we choose green wavelength region, red wavelength region, NIR wavelength region for putting a particular filter into it. So you can see in a picture shown here, this NIR region is showing very bright whitish color. What does it mean? As I was talking about, the scene is mostly composed of the agricultural fields. So you can see the vegetation across there, they reflect very high in NIR region, but you see the similar time, the black regions on the same color in the red band. Why? As I said, the chlorophyll absorbs this particular wavelength region, and using this particular two information of red and NIR, we are able to generate the NDVI and able to know the vigor of the crop. Scientists use this information of green, red, NIR and give some false images, colors to NIR, red and green in a terms. We say many times give a red color to NIR because NIR is not a colorful thing. It is beyond our vision to see. So we give red color. We have a protocol of giving it to NIR. We give what you call green color to red and blue color to green, and create a false color composite where vegetation start looking the reddish color, and that help us giving us the interpreting the data. This particular composition is called false color composite. I would like to bring your attention here that these green, red, NIR, and these regions are transparent region from the atmosphere point of view. But you know, our atmosphere, particularly on Earth, is made up of various gases also, and these gases has their own absorption feature. For example, oxygen, the water vapor, even the carbon dioxide. So for seeing the surface feature, we avoid those regions where these gases absorb. And many a time, the satellite meteorologist, yeah, atmospheric scientists, they preferably choose these wavelengths where these gases absorb, because their interest is to know the atmospheric composition, not the surface. So depending on the kind of scientist we are, the kind of objective we have, we choose spectral windows for our application. You can see this few pictures of false color composite of a reservoir, agriculture region, a south coast of India, and Shivalik Hills in our Himalaya. You see these beautiful pictures seen in different colors, and scientists are trained to analyze this, and they are able to interpret where is crop, where is forest, where is water bodies, and even not only the target and the discrimination, even we are able to know that what is their property, what is their amount, and that's how this remote sensing help in identifying and enumerating the various natural resources. So if I looking this background, this particular image shows you that if you see India in a visible region, that too in a reflection mode, where the sunlight falls and satellite records and create a false color composite. I was telling you, in false color composite, we deliberately give the red color to NIR region. So wherever there is a crop or vegetation, they start looking reddish. So you see India in this fashion, but many a time when we want to know the temperature of our country in terms of the surface temperature or some atmospheric temperature, we use infrared region in emission mode. It looks like the second image shown here. We can take emission mode, only emission of the Earth in microwave region also through a radiometers. They look like this, where the darker regions are regions where there are low temperature as compared to the bright region. Third image you can see here. But this region is also sensitive to water bodies and the water content in the soil, what we call soil moisture. So many of these dark region, black region, are associated with the soil moisture condition, because this microwave region is important region where people estimate soil moisture. The fourth image shown here is the India image from a active system called radar, which was taken by Indian radar system. And since the radar interacts with the surface and the vegetation, and radar has a penetrating capability, many times it can go beneath the canopy and have a scattering. That is why we start seeing the forest different than the croplands, and the radar helps in knowing many areas of crops and forests. One of the advantages of radar, you must be aware that since we have an active system here, we can take day and night imaging. We can take even images even if there is clouds there, because the radar wavelengths of a longer wavelength region like L band and C band, they can penetrate the atmosphere. So all weather capability you have to measure the what you call surface feature, day and night capability. So many a time radars are useful, particularly in monsoon season when we want to see the floods or see how crops are growing. One of the important technique in remote sensing is spectroscopy. Basically, remote sensing is a branch of spectroscopy where you detect this either reflection or emission in different wavelengths. In the given picture, you can see that many a time some minerals which are not distinguishable in the normal red, green, blue image in visible region, if you take their image in a long wave infrared region, they look different. Why they look different? For example, you can see the quartz and feldspar here. You can see their emissivity, the emissive characteristic in a passive domain is different than the other mineral. And many times they are more distinguishable in infrared region. That is why this technique is used to know many minerals in this region. This technique, when employed on the Mars through an instrument called Themis instrument, it was available in Mars Odyssey thermal imaging system. This 9.35 micrometer, 11.04 micrometer, and 12.57 micrometer, the infrared radiations, I mean, emitted radiations were detected, and by giving a proper color to different this wavelength observations, so like you give the reddish color to 12.57, give greenish color to 11.04, and blue to 9.35. This kind of image comes out. And since, as I said, the minerals have a different emissive behavior, the emissivity in these regions, particularly all reddish regions are olivine minerals, where the abundance of olivine is high. So this is the principle by which not only the Earth, we can probe different planetary system. These wavelength regions I am talking about, they are much better for planetary system because many of these wavelengths get absorbed by water vapor in Earth system. So, but where in other planetary system, since there is no much absorption, like in I mean, like in Mars or Moon, this techniques becomes more effective. So let's see one another example how we detect our crops. So we put a spectrometer, either airborne or spaceborne. This is one airborne picture taken by Everest data. Everest is a spectrometer, and what you see is this. Uh, you are seeing a spectral curve, means reflectance at different wavelength at different fields, and you are seeing that their reflectance curve or the signature is changing from field to field. And this particular library, when you have, and you know already that my particular crop has this spectral characteristic, and when we get observation from airborne or spaceborne images, we just try to match them out and do the pattern recognition, and we are able to detect these the crops and their biophysical property more effectively using these principles. So here I want to just simply show you how the principles are used to detect the various target. This is one example where we are seeing a region near the coast, at different wavelength configurations. And what we are start seeing that since this wavelength penetration in the water is different, like blue penetrates more than the higher what you call wavelength region, you start seeing different pictures in the coastal region. And this principle of differential penetration and scattering in water is able to give you various property of coast and ocean surfaces. And that's how it is used in various oceanic applications. Many time here I would like to show you something that while doing crop assessment or monitoring a crop, I'm showing you a crop fields near Pantnagar Agriculture University. If you take a picture at one particular time, many times all these crops look similar. Why look similar? Because they're all greenish. And I just said in false color composite, green color, I mean greenish of crop is seen as a reddish because we give the red color to the near infrared region. So many times the separability, the separation between the identification is not that good. So what we do, we simply take multi-observation, multi-date observation. Instead of one observation like 31st January 2023, I'm showing you on top of it. If you take 25th January, 5 December, and 5 November, what you start seeing is a different color patterns. It is because crop at given moment may give you same greenness, but since their growth patterns are different, so you start seeing them differently. And that is why in second image, you start seeing many crop patterns coming out because of their temporal growth patterns being different. And the reddish ones are wheat crops in those regions. When we employ this space observation from space, this remote sensing observation from space, not only we do very good what you call observations of Earth and their different nature resources, it is very beneficial to even look at the planetary system from the space. Why? Because when we do astronomy from our ground observation, majority of the time our atmosphere plays a hindrance to the observation of telescopic observation. Why? Because as I said, atmosphere has many absorption features. But if you go to the space and go above the atmosphere, our planetary system start looking much more clearer and distinct. And there comes the power of what you call the satellites, even not doing the Earth, but the planetary exploration also. This is one example where the satellite called MRO by NASA. It has a various instrumentation in different wavelength region. Generally, a satellite is composed of different instrumentation placed in UV, visible, infrared, microwave, and they observe the surface. This is one typical example of MRO where Sharad is operating in what you call microwave region, and then there are infrared instruments, MCS, then visible spectrometer, CRISM, high-rise, marquee, CTS. So different, you start scanning or probing a planet into different wavelength region at different spatial and resolution or details to meet the scientific objective, and that's how the different explorations are done. This one small example to prove that concept. It is taken from the Chandrayaan-1 mission, where if you see this particular the observation of Chandrayaan-1 spectrum from their high C instrument, we have put a spectrometer called high C in Chandrayaan-1. So if you see the oriental basin reflectance spectra of different feature, what you see is a what you call plagioclase, pyroxene, highland soil, mare soil. So as what you see visibly is only a shades of color, but when you see spectroscopically, you see 1, 2, 3, 4 this spectrums which are distinct. And these distinctions tell us that we can know about those surface features. For example, the right image, a 3D view of parental basin with high C derived surface composition shows you that if you give different colors, red to 750 by 430 nanometer ratio, green to 750 by 900 nanometer ratio, and blue to 430 by 750 nanometer ratio. If you give these colors, you get this kind of pseudo image. And this images tells you where is the iron, where is the titanium rich surface, where is the glass. So all this spectroscopic observation when placed through a computer processing and pseudo coloration, we are able to know the locations of different surface characteristics and minerals. Now let's talk a bit about the polar orbits. I mean, the orbits in which they are taken. There are various configuration for Earth remote sensing. Many a time we put things in a polar orbit, like the satellite revolves around the pole as the Earth moves. And in this process, we are able to scan the whole Earth surfaces in different swaths. And generally, orbits are placed in such a way that they are sun synchronous, means the sunlight falls equally when they cross the equator. The local times are same. These orbits are called polar orbit. They are very popular orbit. Generally, their height is 700, 800 100 kilometers. And we get to see good details of surface and atmospheric observation. But when we want to see very fast 10 to 15 minutes observation of the Earth, we put our satellite as 36,000 kilometer in equatorial plane. That is called geostationary orbit. In this orbit, what happens? The satellite and Earth rotation becomes similar. It means the Earth becomes stationary to the satellite, or satellite becomes stationary to the Earth in reference plane. So you start seeing the same image. So you have a power to see in different fast time domain. Such geostationary orbits are used for meteorological applications. But for many applications, we use some inclined orbit, which is not totally polar or equatorial. They are inclined at certain angle because it has certain advantage of having more revisits in a particular region when we want. And there are also a low altitude satellites in a range of less than 1,000 kilometers. So depending on the application, we use polar orbit, inclined orbit, and geostationary orbit. And what we place on those satellites are various instrumentations. Initially, we used to place TV payloads. Later on, now a lot of multispectral spectrum. This imagers are placed, which can have 3 to 4 band. Nowadays, even more than that, 10, 12, 13 bands are also placed into that, depending on the wavelength selections you do in different regions. Spectrometers, as I said, spectrometers are there, which takes continuous measurements of reflectance in a wide spectral domain from 400, say, to 2,500 nanometer. And each images are of 10 nanometer interval. So you get a huge information from that. They are not selective in wavelength. They are continuous wavelength in the images into continuous wavelength. They call spectrometers. Whereas in multispectral, one chooses some selective windows. In a spectrometer, continuous scanning of reflectance at different wavelength is done. There are altimeters, there are synthetic aperture radars, there are scatterometers. So various instrumentation put depending upon the kind of application we are doing. So when you observe anything from polar orbits, how they look like, you can just see that depending on the swath, the coverage you want to obtain. Like once we have a satellite instrument called wide field sensor, it can take images of 800, 900 kilometers. You can see whole Uttar Pradesh or northern India seen from there, and then it has a high revisit. It can revisit in 5 days. But many times we want more resolved information. Like we have a very popular instrument called LIS-3, currently very popularly or work hard for our natural resource management. It takes observation of around 23-meter resolution. So it coverage are relatively smaller, 140 that roundabout kilometer swath is there, but it sees more detail. We have a LIS-4 camera which see much more details, even at 5 meter or so. But then its swath is again limited or smaller. And we have an instrumentation which can work in 1 meter, even less than 1 meter. So depending on how detailed you want to see, one can see it. Only the swath becomes smaller. When you see for a larger domain, your swath, you see many areas, but then details loses out. So a scientist chooses to use some configuration. He wants to see details, or he wants to see a larger picture, but faster in revisit. So that's how the polar orbit help us in doing it. And I was talking about the geostationary platform. You must be aware we have an inset satellite. You must be seeing through TV and other coverages when you have to see weather patterns. We have placed this particular orbit in 36,000 kilometers, and from there, as you said, Earth and satellite is stationary. So what you see, the changing patterns of weather in every half an hour and changing patterns of sun. Here, sunlight goes on changing, but Earth remains stationary before the what you call the particular sensor, and this sensor is mostly used for meteorological application. I'll be talking bit more detail later on that what are the application being done from these polar or geostationary orbits. Let's go to a bit of history that how it started. That everything in remote sensing started long back when hot air balloons instruments were placed, and we start seeing the synoptic picture of the Earth. And there we started making maps and start see the Earth feature in a spatial domain. And the basic thrust in this technology came after the launch of Sputnik in 1957, where first artificial satellite was launched. Thereafter, many satellites has gone to it into the orbit, and Aryabhatta is India's first satellite, which was launched in 1975, and Bhaskara was India's first remote sensing satellite, which took observations of Earth features and atmospheric features in 1979 using TV payloads and Samir radiometer. As you are all knowing that, must be knowing that after 1957, the Sputnik launch, India started its own journey of space. And you can see here the Nike Apache rocket launch pad, where various sounding experiments started in Tumba, in what you call near Trivandrum. And Dr. Vikram Sarabhai led the team where the space research started in India. And later on, what you call, we saw that developments of various SLV, satellite launch vehicle, PSLV, GSLV, rockets, and they launched our various satellite missions in our orbits. When you have to do the remote sensing, essentially what it calls for, what are the dimensions? One has to make a sensor, one to put the sensor in satellite, launch it through certain rocket at certain appropriate orbit, as I was talking about, either polar, inclined, or geostationary orbit. Then you have to have a receiving data station or reception. That's the Earth station we call. And once the data is received, they are mostly in digital form. You do digital data processing. And after the data is processed digitally, it goes to the application scientists where they do pattern recognition. They do modeling of these data sets to know the various properties and application. And in the end, it goes into the actual applications. Call it agriculture, call it water resource, call it meteorology, so that the outputs can be useful to management and planning purposes. Why we went for this space research? You must be aware that ultimately any country has to know about its resources and its challenges. And you all know our country looks so beautiful. This picture is taken from the L1 platform at 15 what do you call lakhs kilometer away. And in this whole, you can see this particular hemisphere. The Earth looks so green and beautiful from the distance. And why? Because we have a variety of diversity. We have glaciers, we have coastlines, we have wetland, we have a forest, we have a huge agricultural land, but at the same time, we have a big population to cater with. Now, once the population is there, obviously what it does with the time, resources being same, as population increases, there are declining water, there's land degradation, our forests are reducing because we have to produce more crops. So obviously, many times deforestation take place. Since warming is taking place, we are going through the process of climate change, global warming, the glacier retreats, and many such kind of challenges are also coming to picture. So how do we encounter them? Obviously, one big solution is let's monitor them, let's see them how they're doing. So this remote sensing helps in monitoring our resources, seeing how they're changing, and this monitoring through mathematical modeling and computer simulation also help us to forecast and give predictions that what's going to happen so that a particular management uh, decisions are taken. What are our Indian priorities? Why this particular space mission is done? The main purpose of this space missions are our priorities in field of agriculture, the fisheries, the horticulture, the forest, the biodiversity, the environmental impacts. Disaster is one of the important element whenever there is either the monsoon of season, lot of flood, many time drought. This thing happens, so we have to monitor them. The cyclones are there. One of the challenging area where satellite plays a very important role. Surface water resources, groundwater, weather forecasting, ocean state forecasting. The urbanization is increasing, so we have to do urban planning, rural road networks, climate change. So all these things has to be observed, quantified, and these are our priority areas. Of course, many things are also being done through surveys on ground-based measurement system, but obviously dealing a country of size of India is not easy. That is why the space technology, the space surveillance system, monitoring system plays a very important role. And India has this kind of capability to observe this phenomena regularly. We started quite early, as I said, in 1968 itself, and remote sensing was proposed as a tool for national development. And later on, we conducted experiment of coconut root wilt disease through airborne sensors, of course. And then this particular experimentations yielded into a crop yield assessment and a application-oriented programs. And then in first decade of 1979 to 1990, let me call first decade of remote sensing, although we launched the Aryabhatta as the first satellite, but remote sensing satellite was Bhaskara 1 and launched in 1979, and then it was Bhaskara 2 launched in 1981. And these were the two satellites which gave the what you call the new knowledge to us. It has a TV camera, it has Samir payload into it, and then it was further improved in form of Indian remote sensing satellite further. These were the few observations of Bhaskara initially. And you can see that the brightness temperature, the hot and cold regions of the country, initially taken by a Samir radiometer, and that worked in the micro region. These were some of the pictures of initial Bhai Bhaskara satellite. You can see that in those era, even getting these pictures were a big task. But now the same technology, when improved, the same laboratory, same institute, now can take picture of such a clarity of sub-meter resolution through our new satellite system we call Cartosat series. Second generation was important generation where a lot of development took place in our IIRS system and new experimentation of 1C, 1D took place. And it is also known to be a decade where we had the first ocean color monitor, the ocean monitoring system. Then come the third decade, the 2001 to 2010, in which things were further developed and came into operational phase. And one of the important missions were improvement in our INSEN system. We had a resource set platforms. We had a Cartosat platform. We were observing things at 1 meter or even start observing better than 1 meter. In fact, in this period only, the Chandrayaan-1 was launched. So it was a very happening period, a operational phase. Then comes the fourth decade, that was the last decade, 2011 to 2020. In this, many advanced scientific exploration took place. Some of the notable ones are our radar satellite was launched into this period. A ISRO CNES megatropic satellite for science of climate change and those things were also planned. We have a altimeter in this period, and one of the important mission we all know, Mars orbiter mission, was also planned in this particular decade in 2013. Apart from many experimentation, we had a 3D insert 3D what do you call satellite, which was able to know the vertical distribution of temperature and humidity. The current decade, 2021 to 2030, a lot of plans are there. And at moment, already we have launched a radar satellite and a OceanSat 3 satellite, which is a continuity mission from the earlier one. And in future, we are going to launch a satellite called GISat, NISAR, it is radar in L and S band, and a Trishna satellite. So this is the plan of the current few years. And I would like to quickly go to some of the example of the satellite we launched in these decades. And this is resource set satellite, where we had three-tier system. In this system, it was we were having a capability to observe the details as well as the coarse resolution with high revisit depending on the application. We use them. We call list 4, list 3, and AWIFS cameras. And by this, a lot of agricultural inventory is done, and most of the agriculture inventory per country we do from this particular resource set and its continuity missions. Many of the glaciers were mapped. Most of the glaciers of country are mapped, and they are monitored whether depleting, whether the glaciers are melting or not. And this is all done by the satellite because it is a constant tracking of climate change issues. Where are desertification taking, where the land degradation taking place? As I said, as the population increases, as we are growing more and more crops, there are degradations in some areas. It all had been mapped through satellites. Shoreline changes is a very natural process. Many times anthropogenic activities do these changes, and this need to be monitored. And these satellites are helping, the source satellite helping in seeing how the shoreline change is taking place. Since ocean is a important natural resource, blue economy. Our ocean satellite are constantly doing surveillance from ocean satellites, and you can see the chlorophyll variations. And using these chlorophyll variations, one can compute the potential fishing zone. Where would be likelihood of fishes? This is a continuous program, an operational program where this information is given to fishermen. Current launch of OceanSat 3 satellite, which is a continuity of earlier OceanSat. We have a global observation nowadays, so we can see any part of the ocean of the world and see the chlorophylls and the prospect of fish. Microwave satellite has been an important thing. As I was talking about, microwave regions are a bit transparent to atmosphere. So in the process, various radars were developed from airborne till today, the reset satellite we call, and they were very useful. Already we have launched reset 1 and reset 1A, and there are more planned to go further. These satellites are why important. I was talking about is that they can take day-night capability, and even suppose nowadays a lot of floods are there. How you can see the floods when the clouds are there? Optical sensors are not able to see, and they are able to penetrate the clouds, and we are able to monitor the flood situation. These are some images from the radar system developed by ISRO. I'll just talk quickly about the atmospheric observations, about how we are doing our satellite meteorology quickly. We started long back in 1982, where INSET was first INSET was what we call launched. Then INSET 1A, 1B, 1C, 1D. Then INSET 2 series were there. At moment we have INSET 3 series. So there has been continuity of INSET series, and it will be there in future because monitoring meteorology is an important task for all of us, and particularly when extreme events take place. This was one of the camera from on the INSET, where you can see the whole disk from that 36,000 kilometer. At moment I was talking about, we have INSET 3D imaging, which is continuously monitoring our Earth or the Indian system. It has a sounder, it has an imager. What the sounder does? Sounder has a capability to note the temperature and humidity at different altitude. And how it does? By monitoring our Earth's surface in different spectral regions, column IR, sphere, visible, water vapor, thermoinfrared. Since these images come from different layers of atmosphere, when they when we analyze them, we get different atmospheric structures from there. As we are talking, cyclone is the most important application of insect, where whenever it comes, we are able to monitor them, predict their tracks. I'll quickly come to the planetary aspect of it. After doing a lot of how to call work in the Earth resource management and disaster monitoring on Earth, ISRO also took initiative, and in 2008, Chandrayaan-1 was launched. It has 11 instrumentation with this, and this Chandrayaan-1 success become so huge that it was worldwide recognized for knowing the water, but discovering the water on the uh, lunar surface. And we all know that the discovery of water first time happened from Chandrayaan-1 in details, particularly if you see their information from Chandrayaan-1, all these pole regions showing blue region were found associated with this. And then further, Chandrayaan-2 orbiter provided very good informations of moon from the far side as well as many other regions from the orbiting platform. And I'll just try to summarize this, that knowing the lunar water, the molecules, whether it is totally dry, it has some water molecules. There was a hypothesis that they will absorb in around 2.8 to 3 micrometer. Chandrayaan-1 had M cube camera. We have two cameras, high C and M cube, but high C was only available up to 900 nanometer, so it's 400 to 900 nanometer. But this M cube has a capability to observe at 2800 nanometer also. So this dips in at 2800 nanometer provided information that, yeah, there is what you call the abundance of the OH and H2O molecule in that surface. And later on, a specialized instrumentation in Chandrayaan-2, IIRS, instrument is called IIRS, was placed with the configuring the spectral sensitivity in 3000 nanometer around, or even up to 5000 nanometer, what we call 5 micron, what you call wavelength region. And this dips of this OH and H2O molecule was seen distinctly. And that's how the complete picture is now clear and unambiguous detection has taken place. So a story started in 2008, but now it was proven in Chandrayaan-2 that this particular region has those components. So it was an important mission from that point of view. I was talking about the Mars orbiter mission. It was equally important mission. And you all know that India was one of the first country which in first attempt could reach Mars, and it has five what you call cameras onto into this particular mission. The Mars color camera, the picture what you are seeing here, and another was a thermal infrared spectrometer in which I was working, and I had opportunity to work in that thing. It was a spectrometer working in 7 to 13 micrometer region, in infrared region. It was meant to detect the minerals and thermal characteristic of the atmosphere. Third was the Mars, what you call a methane sensor, and it was aimed to detect the methane, what you call on the Martian surface, because earlier it was envisaged that Mars has a very trace amount of methane. So MSM, that Mars sensor for methane, was done, and then MENCA instrument was there for knowing the exo-atmospheric neutral compositions, and then it was what you call Lyman alpha instrument was there for measuring that D by H ratio. So it has a 5 instrumentation. It was a beautiful mission which gave a lot of information to us. This I'm showing you only a small picture of Earth, I mean, what call one picture of Mars taken from the Mars color camera, and you see the signs of paleo channels and how water would have flown once upon time. It was wet, and that proved that particular theory. And when we worked on this, we could compute even the likely discharges of the region looking at the geometric and morphological characteristic of the floodplains and all these things. So this particular camera helped a lot in knowing the surface, some atmospheric properties, and even some hydrological properties. In future, I would like to just brief you that we are going to have a geostationary imaging satellite called GISAT. This satellite is basically amalgamation of the whatever the instrument we put in our polar orbits but we are going to put into a geostationary platform. So it has a capability of observing in multispectral domain at around 42 meter spatial resolution. Generally, geostationary platforms look the surface at 1 kilometer at the base of that kind of resolution, but this imaging satellite is planned to see 42 meter, what you call spatial resolution, in that too in a multispectral sense that it has a 6 spectral band, as similar to what we put in our polar orbiting. So our capability enhances to a level that we start seeing the polar orbiting, what you call that imaging capability from geo. So what is the advantage? We can see in high resolution at high revisit time. Every half an hour we can take a picture at that high resolution. We have this satellite also has a hyperspectral instrument called HISI. So it can also take a continuous measurement of 158 band in the Vinny region or 256 bands in shortwave infrared region. So it will be one of the unique satellite which is going to be placed in future, and it will able to it will be very what you call important for surveillance and monitoring many of these our nature resources as well as disasters when it happens. And for sake of clarity, I can show you that there was a small experiment done before with a similar instrumentation called GHRC instrument in some other satellite. And you can see with such kind of capability that one can even see a satellite launch, which has happened in Sriharikota from 36,000 kilometers. So it was experimental mission, and it gave this kind of capability. It has a similar instrument. GHRC has a similar instrument like what we are going to have in GISAT. So in future, such capabilities of is going to increase. And further, we have a much better what you call resolving capability at 36,000 kilometers also. So in future, obviously, India has developed, started from Bhaskara 1 or Aryabhatta 1 time scale, and we have come to very what call advanced stage where not only Earth we have seen, we have orbited or we explored the Moon and the Mars. We have started with a few kilometer resolution. Now we can see sub-meter resolutions and very fine details. But in future, what we need is a development of constellations. There will be many satellites together launched because looking at high resolution and high repeat is the requirement. Because many times when we are able to see in high resolutions of few meters, we are not able to see it fast. So this can only happen when we put many satellites together. Hopefully, this would be a direction where things will take place to have a meaningful solution. At moment, what we are retrieving information also has to be improved. There has to be more physics, more mathematics put into the what you call our algorithm, so that we are able to precisely retrieve the information. Monitoring, seeing what you call any Earth or any planetary system is one thing, and retrieving the information is another important aspect. Not only information one has to receive, in actual sense, the information has to go to some model so that this become a total solution. We can even have a forecasting skills. So such experiments are going on. Already many work has done where actual satellites observations are put into mathematical and numerical models, which simulate the futuristic scope of hydrology or meteorology or anything of that type. And then ultimately, Our aim is to have in real-time monitoring and forecast of extreme events and web-based data dissemination so that things are easily available and easily disseminable. So whenever there are disaster, whenever there are the requirement, we have a monitoring system working in a real-time domain so that adequate measure can be taken. Thank you very much.